Пожалуйста, какие здесь есть элементы? А их элементы это кто?
Дымбень чисто вообще вот классика.
Достойно.
Опс. ГГ.
Что-то пропустил?
Ремикс песни. Просто забыл какой.
Надеюсь, герой этой песни не в конфе.
Что за песня? Секрет?
Я могу чисто в чат кинуть эту ссылочку, конечно.
Кидай.
Да не, ее увидит всего 20 человек.
Кидай во флот.
Да. А, подожди, а ты не можешь кинуть в
В
телеге?
личку? Да не, я во флут перешлю лучше.
А, в телеге ж там же все. Да, логично.
Нет. Руслан.
Руслан, если ты нас слышишь, то у тебя микро включен. Понял.
Ladies and gentlemen, hello. Can you hear me? Can you see the whiteboard?
Yes.
hello.
Yes, hello.
Yes.
Yes, yes,
Yes,
we can see it.
Last time we considered three forms of induction and proved that they are pairwise equivalent logically. And now we are going to apply our newly acquired knowledge of induction to some arithmetical matters. That is, we will start considering divisibility theory or number theory, so the very elements of number theory. We will consider today, we will consider integers. You know, intuitively, the set of integer numbers consists of 0, plus minus 1, plus minus 2, plus minus 3, and so on. So we suppose it is intuitively known to you. And by default, every variable today will stand for an integer. So all the domains of predicates will be integers unless specified otherwise. Is it clear? So we will be speaking about integers. Is it clear?
Yes.
Okay.
Yes.
Let me fix it in written form. So by default, every variable today stands for an integer. First of all, what does it mean that one integer divides another one? We say that A divides B, A divides B, or sometimes they say that B is divisible by A, or B is a multiple, кратное is a multiple of A. What does it mean? By definition, that means that there exists some K such that B equals A multiplied by K. Let's consider some examples. First of all, say 2 divides 6. Why is it so? Because it is possible to express 6 as 2 multiplied by what?
1/4.
1? Really?
By 3.
Just
That's 3, of course.
sorry, some guys may say that you're too quiet for now. Could you just add
Adjust
some
the volume,
volume?
please.
Could I do what?
Adjust
Your
the volume.
microphone is a bit silent.
Oh, I don't know how is it possible to be silent a bit. But anyway, can you hear me now?
We can hear, but not very loudly.
Yeah.
Well, I don't know how can I help you. In fact, maybe
Well, you can use the settings, then go to the sound and
I don't think there will be any effect. So can you hear me clearly?
Yes.
So
It was before.
yes.
let's try to be happy with that. Okay, 2 divides -6. Is it true?
Yes.
Yes.
Why? -6 equals to?
Multiplied by -3.
Aha. And what about -2? Does -2 divide 6?
Yes.
Yes.
6 equals -2 multiplied by
-3.
-3. And likewise, -2 divides -6. -6 is just -2 multiplied by 3. And what about 0? Is it true that, say, 5 divides 0?
Yes.
Yes.
Why? Because 0 equals 5 multiplied by 0. And what about 6? Does 6 divide 0?
Except 0 divided by 0.
The same. Okay. And is it the case that 0 divides 0?
No.
No.
Well, it's a problem because it's more undefined. Nobody knows.
There is no problem here. And of course, it's not a situation where nobody knows. 0 is divisible by 0 or 0 divides 0. Why? Just because our definition, look here, that would mean that 0 equals 0 multiplied by something. But can you provide a number which equals 0 when multiplied by 0?
Yes,
Of
we
course,
can.
there are plenty
Anything.
of
Any
such
number.
numbers. Sure.
It's infinity.
So why? No. 0 multiplied by 3 equals 0, isn't it?
Yes, but
So,
well, can we write this then that this 0 equals 0 multiplied by infinity, for example, like infinity instead of numbers? Or
what's infinity? What is infinity? Infinity, it is something, it is not a number. So what's infinity? We use the definition.
okay.
Our definition undoubtedly says that A is divisible by B, B is divisible by A, or A divides B if and only if it is possible to express B as A multiplied by something. It is possible to express 0 as 0 multiplied by something. So,
Excuse me, shouldn't the key belongs to real numbers, or not real, like целые числа?
it is not key, but it is k. And of course, it does belong to integers, to the set of integers. By the way, we have agreed that every variable by default
I'm
stands
sorry,
for
I
an
haven't
integer.
seen this part. I'm sorry.
I see. So, please do not mix division and divisibility. They are similar but distinct. It is not possible to divide by 0. Why? Mainly because this number, this number is arbitrary. So you can't say what 0 divided by 0 equals 2. It can be either 5 or 2021 or whatever. So division of 0 by 0 doesn't make sense, but 0 is divisible. It is divisible, but you can't divide. Of course, there is some similarity in words, but you shouldn't be misled by words and their natural semantics. Use the definition, please take it seriously. Mathematics is all about axioms and definitions, not some connotations of words. So, according to the definition, 0 is divisible by 0. And in fact, every number is a divisor, that is, it divides 0. Every number divides 0. Why? Because for every number, I have that 0 equals A multiplied by what?
By 0.
Of course. So 0 is divisible by whatever number. Do you know a number which divides everything?
1.
1.
1, and in fact, minus 1. 1 divides every number. Why is it so? Because every number A can be expressed the following way. 1 multiplied by A. Is it clear?
Yes.
Yeah. Of course.
So, 1 divides everything, and everything is divisible by 1 divides every number, and 0 is divisible by every number. Something like that. Okay. Now let's obtain some general properties of divisibility. Lemma 1. Lemma 1 says that for every integers a, b, c, first a divides a. Second, if a divides b and b divides c, then a divides c. Third, if a divides b and b divides a, then what?
B equals A.
Not exactly. B and A are equal modular sign. So they are equal up to the sign. They
So-
are either equal or the only difference is the sign.
So can we write like A is equal to the model of B?
Of course, you can say that the absolute value, usually it is called this way, the absolute values of A and B are equal. It is the same. The absolute values are equal. Of course. So let's prove this theorem. For the first one, what do I need? I need to prove that every number is divisible by itself. So let's recall the definition. A must be equal to A multiplied by something. So I want that there exists some k, so that A equals A multiplied by k. Can anybody provide such k?
1.
One is enough. So I hope it is clear. Now I have an implication to prove. So that's given that for some k, b equals a multiplied by k, that is a divides b. For some m, c equals b multiplied by m. And I need to construct some number L so that C equals A multiplied by L. How is it possible to do so? First of all, we notice that C equals B multiplied by M, and then substitute this expression for B here. So we have A multiplied by K multiplied by M. Is it clear?
Yes.
And now we will use some properties of arithmetical operations. Namely, here we will apply the associativity of multiplication. We believe these facts. We don't want to prove them. It is possible to prove them, but then our course would turn into some activity when we are proving intuitively obvious facts. So there will be no new knowledge obtained. We will say establish the facts well known to you. So you will see how it is possible to verify them, but you will gain no new knowledge. And in fact, in our course, we want a good balance between proofs, between verification, and between new facts, new knowledge. So we'll ignore this law. We will take it as given. So we will freely regroup the terms here, applying the associativity law. Is this idea clear?
Yes.
Yes.
So now we have that C equals A multiplied by something. And it is exactly the thing we are required. C equals A multiplied by something. So just take this one for L. Is it clear?
Yes.
Yes.
The third one is a little bit trickier. A divides B and B divides A. So what's given? It is given that there exists some k so that b equals ak. And for some m, a equals bm. As before, we have that b equals a multiplied by k, then substitute this right hand side. So we obtain bmk, okay, and by associativity, b multiplied by mk. Is it clear?
Yes.
So what is the next step?
We should divide by b.
But is it always possible?
No, if b is 0, we cannot.
So we have two cases. Our first case is as follows: when b equals 0. But if b equals 0, then you know a equals b multiplied by m. So this product equals 0 as well. They are both 0, so a equals b, and we are done. By the way, we want that a is either plus or minus b. So we are done here. Is it clear?
Yes.
I hope it is. So the second case is when b differs from 0. If it differs from 0, then it is possible to cancel b in both parts. So then 1 equals m multiplied by k. So what does it mean? Now we resort to the elementary properties of multiplication one more time and conclude that either m and k are both 1 or they are both minus 1. So in the first case, we see that b equals a. And the second case, when we have minus 1, then b equals minus a, or a equals minus b. Anyway, a and b are the same up to the sign. Is it clear?
Yes.
So it is obvious. But let's memorize these three properties. The divisibility relation is reflexive, that is, every number divides itself. It is transitive. If a divides b and b divides c, then a divides c. And it is not antisymmetric, but close to that. If a divides b and b divides a, then the only difference between a and b is the sign. Lemma 2. Lemma 2 describes the relation between divisibility and addition. There is no point in raising your hand, for I have no secretary who could allow you to speak, so I have no time to do it myself. Just speak if you want to say something.
Oh, well, so yes, I forgot that this is our lemma 1 is transitive, non-antisymmetric, and I didn't get the first.
The first one, that a divides a.
And you called it with some term.
You need the name. The name is reflexivity.
I see.
We will come back to this terminology and these notions at a later stage of our course. For now, they are not needed. Okay.
Okay.
If a divides b and divides c, then I say that a divides the sum, b plus c. And likewise, a divides the difference, b minus c. So if both the summands are divisible by A, then the sum is divisible as well. Of course, it is it can be readily generalized to the case when you have more than two summands, say 3 summands and more, because say x plus y plus z is nothing else than x plus y plus z. So you can think about this sum as the sum of two summands. Is it clear?
Yes.
So what's given? We are given that b is a multiplied by k, or simply ak. And likewise, c is a m. What can one say about the sum? B plus c is just ak plus am. And now we want to apply another law of another property of summation and multiplication, of addition and multiplication, namely the so-called distributivity law. We can move a out of the bracket. You should know it well. So BC equals a multiplied by something. So b plus c is divisible by a, and the same for the difference. Is it clear?
Yes.
As a corollary, corollary means следствие, that is something which follows from the previous lemmas, theorems, or a few of them. If a divides a sum, or divides a difference, and a divides the first summand or the second one, doesn't matter in fact, then a divides the other summand. Is this idea clear?
Yes.
Or we can obtain it from the previous one. The main point is to express C as a sum or as a difference. It is quite clear. C is B plus C minus B. Do you agree?
Yes.
So we know that both summands are divisible by A. Both summands are divisible by A. Hence, C is divisible by A as well. Then A divides C by our previous lemma 2. And likewise, in the case of the difference, C equals, what it equals B minus B minus C. And likewise, by lemma 2, we know that B is divisible by A and B minus C is divisible as well. So we see that A is divisible. A divides C. Is it clear?
Yes.
And now let's
Yes, yes.
thank you. So for confirmation,
Can you show the previous lemma, please?
hear you.
Lemma, please.
So, and now we will consider so-called integer division, or division with a remainder. Are you familiar with such concept? Деление с остатком.
Yes.
Yes.
Or целочисленное
Yes.
деление. And now we want to firmly establish
Yes.
the respective theorem. We will prove it formally that there indeed exists a partial quotient and a remainder, неполное частное и остаток. First of all, let's consider some example. Say we wanted to divide 10 by 3. 10 is not divisible by 3. But nevertheless, we can say that 10 equals 3 multiplied by 3 plus 1. And here 1 is what?
Remainder.
1 is the remainder. 1 is strictly less than this number, which we divide by, and greater or equal than 0. But is it possible, say, to divide 10 by minus 3?
Yes.
What the result will be?
Yes.
Minus.
We can take 4 here and obtain minus 12. Minus 12 is less than 10. Likewise, in this situation, 9 is less than 10. And here, excuse me, it is minus 10, of course. Minus 10. Minus 10. Of course, it is possible to divide 10, but then you will obtain minus 3. It is not interesting. Let's divide minus 10 by minus 3. Or not by minus 3, but by 3. Oh, that's better. Let's divide it by minus 3. Minus 10 by minus 3. If I multiply minus 3 by 4, I will obtain minus 12. Minus 12 is less than minus 10, but the difference between these two is not
2.
Of course, it is 2, and 2 is less than what? It is less than 3, it is less than the absolute value of our divisor. Is this idea clear?
Yes.
Yes, and then just
Yes.
and we can say that this is a common principle in mathematics. So just this is yes.
So the general principle is that the remainder must be less than the absolute value of the divisor,
Okay,
but still not negative.
So that's for mathematics. Okay.
I think this generalization is too far-fetched. So in the whole mathematics, not merely divisibility theory, but nevertheless.
No, I just sometimes know that there's some can be difference between.
Nevertheless, let's
So,
take the theorem.
so the remainder had be more than 0, yeah?
Of course, the remainder is always non-negative. It can equal 0, but it can not go below 0. It is non-negative. Non-negative.
Okay, thank you.
So how is it possible to state and prove the theorem formula? We will do it in 2 steps. The first step will be our theorem for just natural numbers. And then after that, we will generalize it to all integers. Why will we do it this way? Because for naturals, we have induction, and induction is a very powerful principle. We will use induction almost everywhere. So for every 2 natural numbers a and b, they are not arbitrary integers, but naturals, where b is not 0, it is not possible to divide by 0. Still, it is not possible, even in our course. A number might be divisible by 0. In fact, only 0 is divisible by 0. But it is not possible to divide by 0. For every 2 a and b, where b is not 0, there exists a unique pair. Here we have some new object, an ordered pair of q and r of 2 naturals, n squared. Is it clear what does it mean? What it means?
Not really.
Not really. And what is R squared? What is R squared? R squared is a set of all ordered pairs. We will define this concept formally a little bit later. This is the set of all possible pairs of real numbers, like plane coordinates, They are ordered. That means that this pair 0, 1 and the point 1, 0, they are distinct. Is this idea clear?
Yeah.
Yes.
Have you had coordinates on the plane? Cartesian coordinates. Декартовые координаты.
Yes.
So, but now we want an ordered pair of naturals. And this sign is for saying that this pair is unique. This pair is unique. There is one and only one such pair. Which pair? Such that A equals BQ plus R, and R is between 0 and B. Is it clear?
Maybe module of B.
Not module, because our, by the way, it's called absolute value, usually. And we will use the word module or modulus, it is Latin for some other idea. It is not needed here to speak about absolute values, because B is a natural number whose absolute value coincides with itself. Is it clear? These are naturals, that is non-negative numbers. So I hope it is clear. How is it possible to prove that? Principle. I will use its. Can you hear me?
Yes.
Yes.
Or Zoom has informed me that my connection is unstable. That's strange. The least number principle in its form for sets says that for every set of natural numbers, if this set is not empty, then there exists such a number which belongs to X, so that every number which is less than n, does not belong to X. Or otherwise, I can state it the following way. There exists the least or the minimal, which are equivalent in this case, the least element in X. Is it clear? For whatever non-empty set of naturals, there is the least number, the smallest one in this set.
Yes.
This was our least number principle, and we applied for the following set. Let X be the following set. It is the set of all naturals such that A multiplied by this S, B multiplied by this S is greater than A. Why so? What is the main idea? The idea is as follows. We want to find 3 as the quotient. How is it possible to do so? we will consider numbers like 3 multiplied by something. 3 multiplied by 0 is what? It is 0. So the difference is 10. 3 multiplied by 1 is how many?
-3, -3.
-3, so here we have 7. 3 multiplied
7.
by 2, we have 4. So all these numbers are positive and in fact greater than 3. 3 multiplied by 3 gives us 1, and 3 multiplied by 4 gives us -2, which is less than 0. Is this clear? Is it clear?
Yes, yes.
So our main idea is to subtract 3 until we will obtain a negative number. Until we will obtain a negative number. So formally, we do the following. First of all, let's consider the set of all naturals such that b multiplied by s is greater than a. Is this set empty or not? Is it possible to exceed a by taking b a few times? Is it possible to exceed a?
Yes.
Why? Which number is greater than a? I say that b multiplied by a plus 1 is greater than b multiplied by a. Do you agree?
Yes.
Why is it so? Because multiplication by a positive number, as b is greater than 0, then from the fact that x is less than y, it follows that bx is less than by. Do you agree? It is another property of multiplication. Multiplication is monotone. When you multiply by a positive number, is it clear?
Yes. Yes.
So this one is greater than BA. But we know that B is at least 1 because B is positive. B is positive. Do you agree?
Yes, and
Yes.
because we take natural numbers which are
Of course.
also
So-
integer ones.
So we have that this number b multiplied by a plus 1 is greater than a. So we have at least one such number. A plus 1 belongs to the set x. Is it clear? Then x is not empty. And if x is not empty, we can say by applying the least number principle, we can take the least number in x. By the least number principle, there exists some s prime, so that s prime is the least possible element in x. So let me write it one more time. It is the least number with the following property. A is less than b multiplied by such number. Is it clear?
Yes.
So x is not empty. So here we have the least element in x. What this element can be? What can this element be? The first case, is it possible that s prime is 0? If s prime is 0, you know s prime is the least number with such property. So a is less than b multiplied by 0. That
No,
is
it's
A is less than 0.
It's not possible.
It is not possible. There is no natural number less than 0. So the first case is not possible. What is the second case? If a natural number is not 0, then it is a successor. There exists some k so that S prime equals k plus 1. Do you agree? Not
Yes.
k, but q. We will take such q as the q we need. This is the q we need. We want to prove that there exists some appropriate q. What do we have? You know that S prime belongs to X, so that S prime is Q plus 1. It belongs to X, so A is less than B multiplied by Q plus 1. But what do we know about Q? Q is less than S prime. So Q does not belong to X, because S prime was the minimal, the least number in X. Is it clear? It is the least one. No less number belongs to X.
Yes, it's clear.
So Q doesn't belong to X. What does it mean? So it is not true that A is less than B multiplied by Q. It is not true then. That means that A is greater or equal than BQ. So we have found a number Q, so that BQ is less or equal than A. So then, if we take A minus BQ for A, we will automatically obtain that this R is greater or equal than 0. Is it clear?
Yes.
But why R is less than B? That's the question. Why R is less than B? We need it after all. Let's prove it. What if it is not? What if it is not? Okay. Let's assume that R is greater or equal than B. So A minus BQ is greater or equal than B. Then A is greater or equal than B plus BQ. Do you agree?
Yes.
So A is greater or equal than B multiplied by Q plus 1, which is B multiplied by S prime. But B multiplied by S prime by Q plus 1 is greater than A. So it is greater than A. Clearly, we have got a contradiction. A is greater than A. That's not possible. Is it clear?
Yes.
So let's review our proof. We have considered the set of all natural numbers such that BS is greater than A. We have taken the least such number and see that this number is of the form Q plus 1. For that Q, we have obtained that the difference between A and BQ, which we have called A, is non-negative, but still less than B. So we have proved the existence of an appropriate pair QR. Is it clear?
Yes.
The existence has been established. But what about the uniqueness? Why such a pair is unique? Okay,
Because we have only one minimum number in our list.
of course, but maybe taking this list number is not the only way to construct Q and R. Why Q and R? The theorem requires are unique. Why Q and R are unique? Why is this pair, namely, it is a single object? Why this pair is unique? If it is a question, so why is it unique? Let's prove it. Assume that there are two pairs QR and Q prime R prime ST that is such that both are suitable. That is A equals BQ plus R and R is between 0 and B. And likewise, A equals BQ prime plus R prime and R is between R prime is between 0 and B. So we have assumed that there are two good pairs. Two pairs which satisfy the requirements of our theorem. Is it clear?
Yes.
And now I shall prove that Q equals Q. I'll prove that Q equals Q prime. Then, of course, we will have that R equals R prime. Is it clear?
Yes.
Assume that Q is not equal to Q prime. Then, you know, Q is either greater than Q prime or is less than Q prime. Do you agree?
Yes.
But these two cases are almost the same. They're similar. They're symmetric. So it's clear that it is enough to consider just one of them. So in such a case, in mathematics, they usually say something like that. Without the loss of generality. Without the loss of generality. Or сокращенно WLOG, it is standard. Without the loss of generality, assume that Q is less than Q prime, say. Because the other case is similar. Assume that Q is less. If it is less, then of course, Q plus 1 is less or equal than Q prime. What do we have after that? Let's consider the difference between R and minus R. You know, R equals A minus BQ, while my R prime equals A minus BQ prime. Do you agree?
Yes, it's obvious.
This follows from our assumption. And then we have that it is just BQ prime minus BQ, or B multiplied by Q prime minus Q. You know, Q prime minus Q is greater or equal than 1. So we have here at least B. R minus R prime is at least B. But if it is so, then R is at least B plus R prime. R prime is positive, so this is at least B. But we know that A is less than B. Here we have got a contradiction. Is it clear?
Yes, this.
So we have successfully proved that if Q does not equal Q prime, then one of them is greater, and we can obtain a contradiction. So in general, we established our theorem for natural numbers. For every two naturals A and B, where B is not 0, it is possible to uniquely determine Q and R. Q is called the partial quotient, неполное частное, partial quotient, and R is called the remainder, as it remains after the division. Is it clear?
Yes.
Yes.
And now I want to generalize this theorem to arbitrary integers. Let's do it. As a corollary, we will obtain the following. For every two integers A and B, where B does not equal 0, there exists a pair of Q and R, where Q is an integer, not necessarily a natural number, while R is still a natural, such that A equals BQ plus R, and R is between 0 and what? And what?
B
Not B.
in modular.
The absolute value of B. By the way, this set is just the set of all pairs, all ordered pairs, where X is an integer, an arbitrary integer, and Y is a natural number. So the set of all pairs where Q comes from Z and R comes from N. And such a pair is unique. Okay, let's prove it. The first step is as follows. Let's divide. First of all, let's divide the absolute value of A by the absolute value of B. Why is it possible? Because both are naturals. So by the previous theorem, there exists a pair QR. There exists a pair QR of two naturals. In fact, this pair is unique, but it doesn't matter. There exists a pair of two naturals Q and R. Let's call them Q prime and R prime. So that A equals the absolute value of A equals the absolute value of B multiplied by Q prime plus R prime. And R prime is between 0 and the absolute value of B. Is it clear?
Yes.
So, what have I done? I have applied the previous theorem to two natural numbers, the absolute value of A and the absolute value of B. I have divided the absolute value of A by the absolute value of B, and I have obtained some quotient, some partial quotient Q prime and some remainder R prime. R prime is not negative and less than the absolute value of B. And now I want to construct A and B. How is it possible to do so? The ineffective way to obtain the proof is to consider many cases when A is negative and B is positive and so on. A more efficient way is as follows. Do you know the sine function? Sine.
Yes.
Which values does it take?
From -1 to 1.
1 and -1. I don't like 0 here. If x is non-negative, then it will be 1. And if x is negative, it is -1. And I have the following simple formula. Every number equals its absolute value multiplied by its sign. Do you agree?
Yes.
And of course, as this sign is non-negative, it is possible to divide by it. So now let's consider this formula. What is the absolute value of A? It is A divided by its sign, which equals B divided by its sign, multiplied by Q prime plus A prime. Do you agree?
Yes.
Or one can put it the following way. Or B multiplied by the sign of A over the sign of B, Q prime plus R prime, the sign of A. Isn't that the expression for A we are required? What if we take this one for Q? And this one for A? Is it possible? By the way, we need A being equal to BQ plus R. Of course, we can take this one as Q because Q is an arbitrary integer. But can we take this one for A?
If it is,
No.
if sign A is -1, we could not.
Aha, the problem lies in the sign of this term. Okay, let's analyze it. In fact, we have a good case and not that good. The first and good case is as follows. When A is greater or equal than 0, or R prime is 0, then in this case we will have that R prime multiplied by the sign of A equals R prime. Do you agree? If the sign of A is 1, it is evident, and if R prime is 0, the both sides are 0 for whatever value of for whatever sign of A. Is it clear?
Yes.
But we know that R prime is between 0 and the absolute value of B as required. So then we can take this, the sign of A, the sign of B. We can take this one for Q and take this one for A, and everything will be okay. Is it clear? Then we have successfully divided A by B. Do you agree?
Yes.
What is, well, Yes, you maybe have this sign A may be positive one and A can be -1. But if, for example, we get this sign A from the okay, that we will get this sign A out of the brackets, like sign, and then in the brackets we have B is multiplied by the fraction 1 divided by sign B, and multiplied this fraction by Q prime, and then plus R prime. So if we have the sign A out of the brackets, then we can multiply it and it will be the same. I just don't see the difference and the problem.
The difference between what?
We consider two cases, and then we tell that
You don't see the problem. The problem is that this term, this one, the purple one, this term can be negative. This one can be negative.
And but if we get out this sign
we need a positive value for A. For A, we need a positive value.
And in the end, so we have two variants. R is could be positive, or we have a variant when R with just this apostrophe is
Prime.
Prime, do you mean?
with prime, yes. We have two variants now. R will be in one case a positive, and R with this, I forgot the name.
Up to now, we have considered just one case when either A prime is 0 or A is greater or equal than 0. In this case, we have that this one equals A prime. A prime belongs to the required range and everything is okay. Is it clear? Here we have that R is greater or equal than 0, but less than the absolute value of B. What do you think?
I guess it's fine, we can continue.
Okay. But what is the second case? Let's use some logic. What does it mean that this disjunction is false? What does it mean?
It means that A is less than 0 and
A is negative and R is positive. You know, R prime cannot be negative. R prime cannot be negative. If it is not 0, then it is positive. Is it clear?
Yes.
And then we will continue with this equation, and we will use a very simple trick. A equals, let's write it one more time, B, the sine of A over the sine of B, Q prime, plus R prime by the sine of A. I will do the following. I will add and subtract the same value. It is the module, that is the absolute value of B. First of all, I will subtract the absolute value of B, or B over the sine of B, and then I will add it back. Do you agree that this equation holds?
Yes.
And now, what do I have here? Here I have minus 1 plus Q prime over the sine of B This is the coefficient at B. Plus what? Plus the sign of the absolute value of B minus R prime. Why? Where is the sign of A? Where is the sign of A? The sign of A is -1 in this case.
And now it is in our brackets. Yes.
Because the sign of A is -1. Because A is less than 0. Is it clear?
Yes.
So what do I have here? Here I have B multiplied by some Q. And this one is R I required. Let's prove that this R is as we need. Let's prove it. First of all, you know, R prime is positive in this case. R prime is positive, then our R, which is the absolute value of B minus R prime, it is strictly less than B. Do you agree?
Yes.
On the other hand, we know that R prime is less than the absolute value of B. If it is less than the absolute value of B, then our R is positive. So R is greater than 0, but less than B. And of course, it is greater or equal than 0 and less than the absolute value of B. Is it clear?
Yes.
So I have successfully constructed both Q and R. The only thing which remains to be proved is the uniqueness of our pair QR. Assume that there are two such pairs. So uniqueness. Assume that we have two such pairs. So A equals BQ plus R, and R is between 0 and the absolute value of B. And on the other hand, A equals BQ prime plus R prime, and R prime is in the same range. Is it clear?
Yes.
The idea is the same. Let's consider the difference between R and R prime. And in fact, the absolute value of that difference. That is A minus BQ minus A minus BQ prime. So what? What is it? A is cancelled, so we
BQ
have something like that. Is it clear?
Yes, it is.
Do you know that the absolute value of a product is the product of absolute values? Don't you?
Yes.
Yes, quite obvious.
It is obvious. You can check. So we see that this difference equals the difference between the remainders is the difference between the quotients multiplied by the absolute value of B. Interesting. What if Q does not equal Q prime? Then the difference, the absolute value of the difference is at least 1. Do you agree?
Yes.
So then the difference between R and R prime is how many? It is at least the absolute value of B. Do you agree?
Yes.
Yes.
So then R and R prime are not equal. They are not equal, and then without loss of generality, we can assume that R is greater than R prime. Or otherwise, of course, then R prime is greater. Then R minus R prime equals the absolute value of this difference, which is greater or equal than the absolute value of B. So R is greater or equal than the absolute value of B plus R prime, which is of course greater or equal than B, that as the remainder is a non-negative number. It is not negative. So we have that R is greater or equal than B, which is not the case. We have assumed that Q differs from Q prime. Then we will have obtained a contradiction. So in fact, Q equals Q prime, and of course, R is uniquely determined by Q. So then R equals R prime. Is it clear?
Yes.
So we have proved a very important yet quite easy theorem, that it is possible to uniquely determine both the partial quotient and the remainder for whatever integers, of course, given that the divisor B, that is not zero. How is it practically possible to divide one number by the other one? The main idea is as follows. If you somehow provide Q and R, you can be sure that this choice is unique. So, for example, let's divide -5 by -2. Here we need some Q and some R. So that R is less than 0, greater or equal than 0, but less than what?
Minus.
No.
Yeah. The
Modulus of
absolute
minus.
value.
Yeah.
The absolute value, less than 2. So can you say guess such numbers?
Because Q can be 3 and R should be
3,
1.
then we will have -6, and the difference is 1. So, and according to the theorem we have just proved, there are no other number, no other pair. In fact, our theorem provides an algorithm to divide. For integers, you should divide the absolute values and then manipulate with signs. For naturals, you have to find the least element in X. How is it possible? Of course, the most obvious way is to increase this S step by step until you will find the first number for which this is true, and the previous one is the required Q. So in order to divide, you have to subtract many times, something like that.
And can we go from, not from Q, but from R?
From R, in principle you can. In principle you can, but how is it possible to guess R more effectively than Q?
just
But anyway, now we are not interested in an algorithm. It is, in fact, it is clear that it is possible to extract one from our theorem, but formally we are not obliged to do so. If we can say guess the values, so they are unique. Now we are sure in that. And despite it is undidactical, it is a bad pedagogical practice. Nevertheless, I want to finish the lecture with a new definition. This definition is very important, and you will come across it at the seminar. It is the definition of so-called congruence of two numbers. Two numbers are congruent to each other modulo some other number. Let m is an integer greater than, say, 0. This number will be called the modulus. The modulus. So we say that A is congruent to B modulo M. They pronounce it the following way. A is congruent to B modulo. It is an indirect case from Latin, modulo M. A is congruent to B modulo M. That means a very simple thing. The difference of A and B is divisible by M. Of course, it is not the thing you have expected. So we will prove the following lemma. A is congruent to B modulo M if and only if A and B give the same remainder, after division by M. Is it clear? We say that two numbers сравнимы по модулю M, если их разность кратна M. И это равносильно тому, что они дают одни и те же остатки при делении на M. But by definition, two numbers A and B are congruent modulo M if and only if their difference is divisible by M. In some situations, this definition is more convenient. In other situations, it is better to use the equivalent one. That is, A and B give the same remainder after division by M. The remainders are the same. Is it clear?
Yes.
We will consider this congruence in more details next time. Do you have any questions? Do you need
right after reminder?
After here? So what is this word? The same remainder after division.
Okay, after. I see. Thank you.
After division.
And
so the remainders are the same. Do you need a copy of our whiteboard?
Yes,
Yes,
of course.
yes.
So I'll send it to our chat. So please get ready to take it. I've sent it, so please copy.
Thank you quite a lot.
Thank you. Any more questions? Thank you, ladies and gentlemen. Goodbye.
Thank you. Goodbye.
Thank you. Goodbye.
Thank you.
Thank you.
Bye.
Goodbye.
Goodbye.
Bye.
Thank you. Goodbye.
Goodbye, ladies and gentlemen. Have a nice day.